So let's modify the overall claim by subtracting the lower order term on the right hand side. So we are going to try to prove that for large enough values of n, there exist two constants c and b, both of which are positive, such that once n is large enough, that is, it crosses some positive threshold n naught, t of n is bounded from above by c times n square minus this lower order term. So how will subtracting a lower order term help? Well, we'll see that when we subtract a lower order term, when we use the induction hypothesis to substitute the right hand side here in place of this term, that subtracted lower order term will be getting multiplied by 4, and so the overall value of this right hand side will hopefully come down sufficiently so that we would be able to prove the original claim. So let's see if that works. If not, we'll see if adding a lower order term works. So let's prove the base case here. At n equal to 1, is it true that t of 1 is less than or equal to c times 1 square minus b times 1? Well, t of 1 is 1. C times 1 square minus b times 1 is c minus b. So this inequality will be valid if c is greater than or equal to b plus 1. That is, if we take the number line and let's say this is 0, we know that both these constants need to be positive. So both b and c must lie to the right of 0. And this constraint says that c needs to be at least 1 more than b. So if b lies somewhere over here, c needs to lie to the right of b, such that the distance between c and b is at least 1. Under this constraint, this claim will be true at n equal to 1. Let's assume the induction hypothesis over here. Let's assume that for all values of k less than n, that is varying from 1 to n minus 1, this overall claim holds for t of k. That is, t of k is less than or equal to c times k square minus b times k for some positive constants c and b. Can we prove that this claim holds even at n? That is, can we prove that t of n is less than or equal to c times n square minus b times n? That's what we're going to try to prove in the induction step. We need to prove that t of n is less than or equal to cn square minus bn. Let's start with the left hand side. T of n by definition is 4 times t of n by 2 plus n. Now we can apply the induction hypothesis to say that t of n by 2 must be less than or equal to c times n by 2 squared minus b times n by 2, assuming that n by 2 lies in this interval from 1 to n minus 1, which it will if n is greater than or equal to 2. So for n greater than or equal to 2, t of n by 2 can be replaced by c times n by 2 squared minus b times n by 2. So we don't need to prove any additional base cases because we can apply the induction hypothesis if n is greater than or equal to 2. And for n equal to 1, we have proven that this claim holds, assuming that this previous constraint is satisfied. C needs to be at least B plus 1. So applying the induction hypothesis here, we can substitute T of n by 2 by the right hand side of this inequality, and we'll get C times n by 2 squared minus B times n by 2. And by replacing this term by the right hand side of this inequality, we are making this expression larger because the right hand side is larger than the left hand side. So we'll get T of n is less than or equal to 4 times the right hand side of this inequality, and this plus n remains as it is. Now 4 times C multiplied by n by 2 squared is Cn square, because this 4 will cancel out with the 4 in the denominator. So we get Cn square. This 2 will cancel out one of the 2's here, and we'll get minus 2bn. This plus n will remain as it is. Now we want to prove that T of n is less than or equal to Cn square minus bn. So let's write Cn square minus bn separately, and let's write whatever terms remain separately. So if we split this minus 2bn into minus bn and minus bn, this is what we want to prove on the right hand side. This is what we want to get on the right hand side. T of n needs to be less than or equal to this term. But we also end up with these two terms, minus bn plus n. So when will T of n be less than or equal to Cn square minus bn? Well, if the remaining terms end up being negative, that means T of n will be less than or equal to Cn square minus bn minus some number. So if T of n is less than or equal to Cn square minus bn minus some number, it must be less than or equal to Cn square minus bn as well. So let's impose an additional constraint that minus bn plus n needs to be negative, or at least less than or equal to 0. So T of n will be less than or equal to Cn square minus bn if minus bn plus n is less than or equal to 0. This means bn needs to be at least as large as n, or b needs to be at least 1. So if b is greater than or equal to 1, and if c is at least as large as b plus 1, that is, if we take b to be equal to 1, c needs to be at least 2. So let's say b is equal to 1 and c is equal to 2. For these two values of the constants b and c, we have effectively proven formally that for all values of n greater than or equal to 1, so this n naught is 1, for all values of n greater than or equal to 1, T of n is less than or equal to 2n square minus n, substituting c as 2 and b as 1. So if T of n is less than or equal to 2n square minus n, we can also claim that for large enough n, this right hand side must be in turn less than or equal to, say, 2n square. In fact, it will be true even for n equal to 1. If T of n is less than or equal to 2n square minus n, T of n must be less than or equal to 2n square as well. This means T of n is bounded from above by a constant multiple of n square. So we have proven that T of n is in big O of n square. Again, this proof was not straightforward, because when we tried a straightforward approach of trying to prove directly that T of n is less than or equal to some constant multiple of n square, the proof did not go through. So we had to again subtract a lower order term. You can actually verify that if we had added a lower order term, if we had made the original claim T of n is less than or equal to Cn square plus some Bn. Let me do that in a different color. So let's say we had modified this claim by adding a lower order term. The claim wouldn't have gone through again because we would have liked to prove that T of n is less than or equal to Cn square plus Bn. But when we try to prove that, we would have substituted T of n by 2 by C times n by 2 squared plus B times n by 2. So this would have then been, going back to this proof, I'm ignoring the base case here. In the inductive step, this would have been a positive sign instead of a negative sign. And so we would have got Cn square plus 2Bn plus n, which could have been written as Cn square plus Bn plus n. And we would have liked to prove that T of n is less than or equal to Cn square plus Bn. That is, we would have liked to prove that T of n is less than or equal to this expression by itself. But we end up proving that T of n is less than or equal to this expression plus this other expression, which is positive. This is positive because B is a positive constant and n is positive. So if T of n is less than or equal to Cn square plus Bn plus some positive number, is it necessarily less than or equal to Cn square plus Bn? Well, not necessarily. So again, the proof wouldn't have gone through if we had chosen to add a lower order term. It's only when we subtracted a lower order term that the proof went through. And that's because even though in our original claim we subtracted this lower order term once, but when we apply the induction hypothesis and replace it by replace T of n by 2 by C times n by 2 squared minus B times n by 2, this negative term would have gotten multiplied twice. 4 times. And that would have drastically brought down the value of this expression, making it reasonable for us to prove that this resulting expression is less than or equal to Cn square minus Bn. So we have proven that T of n is in big O of n square. We need to prove that T of n is in big omega of n square as well. So let's try to prove by induction that T of n is in big omega of n square. More formally, we need to prove that there exists a positive constant C such that for large enough values of n, larger than some positive threshold n naught, T of n is bounded from below by a constant multiple of n square. This is what we need to prove. Now, this is a separate proof from proving that T of n is in big O of n square. So we don't have to start out by subtracting a lower order term here. This proof may very well go through pretty simply. So let's try to prove this claim more formally using straightforward induction. So what will be our base case? Let's see if the claim holds at n equal to 1. Is T of 1 greater than or equal to C times 1 squared? That is this claim true at n equal to 1? T of 1 is 1, C times 1 square is C. So this will be true if C is less than or equal to 1. So our induction hypothesis will be that for all values of k in the range 1 to n minus 1, t of k is greater than or equal to c times k square. And we need to prove in the induction step that the claim holds at n as well. That is, t of n is greater than or equal to c times n squared, this same constant c. So this is true for some positive constant c, and we want to prove that even at n, t of n is greater than or equal to that same constant c times n square. Now t of n is given to be 4 times t of n by 2 plus n. Now assuming again that n is greater than or equal to 2, we can apply the induction hypothesis to claim that t of n by 2 is greater than or equal to c times n by 2 squared, assuming that n by 2 falls into this range, which it will if n is greater than or equal to 2, as we saw a few minutes ago. So by replacing this term t of n by 2 by the right hand side of this inequality, we will be decreasing the value of the right hand side here. So the right hand side will then become less than or equal to t of n. The resulting right hand side is 4 times c multiplied by n by 2 squared plus n. And this is cn squared plus n. So we have proven that t of n is greater than or equal to cn square plus n. We wanted to prove that t of n is greater than or equal to cn square. And that trivially follows from this, because if t of n is greater than or equal to cn square plus n, cn square plus n is greater than or equal to cn square. So t of n is greater than or equal to cn square. This means that we have shown that for all values of n greater than or equal to 1, for all values of n greater than or equal to 1, t of n can be bounded from below by some constant multiple of n square. Now this constant c needs to be less than or equal to 1. That is the only constraint on c, apart from the fact that it needs to be a positive constant. We didn't get any additional constraint on c from here because this claim is always going to be true. So if we choose c to be equal to 1, for example, then the claim is actually true, or we could choose c to be 0.5. So there does exist a c that's greater than 0 such that for all values of n greater than or equal to 1, t of n is bounded from below by a constant multiple of n square. This means that t of n is in big omega of n square. And having proven earlier that t of n is also in big O of n square, we have managed to prove the original guess as correct. We guessed that the solution to this recurrence is theta of n square, and we have proven both these claims. We have proven that t of n is in big O of n square, and this was not a straightforward proof. We had to subtract a lower order term. When trying to prove this using the substitution method, this was pretty straightforward. So straightforward induction on the original claim was able to prove that t of n is big omega of n square. So this is how we apply the substitution method to prove our original guess to be correct, which we could have directly proven by master theorem, But just as additional practice with such an example where we have to subtract a lower order term, where straightforward induction does not succeed, we went through this whole exercise of applying the substitution method to prove the same thing that we proved earlier using master theorem.